Okay, next topic is projectiles. So this is going to bring in some Suvat equations and some resolving forces, really. So all stuff you've seen before. We're going to start with horizontal projection because it's a nice easy place to start with these. And the thing to realise with projectiles is that the horizontal motion of a projectile is modelled as having constant velocity. And so the acceleration is equal to 0 because there's no forces acting horizontally. Obviously, we're not considering air resistance here. So that's the thing to watch. So we're really modelling as a particle still. And the vertical motion of a projectile is modelled as having constant acceleration due to gravity. So gravity is acting downwards. So vertical motion, A is equal to G. In both cases, acceleration is constant, so we can use Suvat equations. And they're all in the formula book if you need a reminder of those. I'm not going to write them all out. So the only force that we're really considering is the weight or acceleration due to gravity acting on the particle. So first example. Let's make sure I'm lined up. We've got a particle is projected horizontally at 25 metres per second from a point 78.4 metres above a horizontal surface. So you might want to draw a sketch. I'd probably recommend drawing sketches, but you'd expect that. The time taken, we want to find the time taken by the projectile to reach the horizontal surface. So we're looking for t, and it's been projected horizontally, so 25 metres per second horizontally, and it's going to drop 78.4 metres. The path of a projectile is a parabola. So you'll see that as we go through. So again, we're looking at resolving vertically and horizontally. And because I've got some information about the vertical displacement, I'm going to resolve vertically. And because it's travelling down, if I take my positive direction to be in the direction of motion, then that will make things a lot easier. So resolving vertically. And then just jot down everything you know. So we're moving, displacement will be plus 78.4, if positive is down. Acceleration due to gravity will be 9.8 if positive is downwards. The initial velocity vertically is 0 because the initial velocity on this one is horizontal. So u is equal to 0 and we want t. And so then it's just choosing the appropriate Suvat equation. So you would use S equals ut plus a half a t squared for this one. S is 78.4. U is 0, so that's going to equal 0 plus 4.9 t squared. When you divide 78.4 by 4.9, you get 16. And the square root of 16, we're only taking the positive square root because we want the time to be positive. So t is equal to 4. But you can see there that this displacement is a quadratic equation. T equals minus 4 would sort of take you back that way over to here, but we're not going into negative times, so it's fine. And then to find the horizontal distance travelled by x, you resolve horizontally. And horizontally, you'll get used to this. We want s. U horizontally is equal to 25. The acceleration is equal to 0. We now know that t is equal to 4. And we're looking for s. And so when you use s equals ut plus a half at squared horizontally, because the acceleration is 0, the displacement s is just equal to the velocity times time, and the velocity will be constant in a horizontal direction. So displacement is 100 meters. We're very much back into standard index units as well now. I know we're not always at maths, but we are now. So that's that one. Second example. We've got a particle projected horizontally, velocity of 15 meters per second, and find the vertical and horizontal components of the displacement after 3 seconds. So this is just kind of thinking, okay, after 3 seconds, the projectile might have got to here, and that's all we're interested in really for that one. So we can resolve vertically and horizontally again. So resolving horizontally, we want the horizontal component of the displacement. So we want S, U is equal to 15, A is equal to 0. You could probably stop writing in all of this. It's kind of why I paused really on this one. But you're basically using S equals UT. So S equals UT because the acceleration is 0. And so S is equal to 15 times 3, which is 45 meters. So that's the horizontal component of the displacement after 3 seconds. And then resolving vertically, again we want S, but this time U is 0, A is 9.8. So again we're taking the positive direction as being 0, and T is equal to 3. Positive direction as being 0, the positive direction as being downwards. And we're in this same Suvat equation as the last one. And so S is equal to UT, but U is 0. So it's a half times 4.9 times, so half times 9.8 is 4.9 times 3 squared. And so S is equal to 44.1 meters. So what that means is after 3 seconds, this projectile has moved horizontally. So the distance across here will be 45 meters. So that's your horizontal component. And then the vertical component here will be 44.1 meters. And then part B of this example is the distance from point of projection after 3 seconds. Probably should have written this on earlier. So distance from point of projection after 3 seconds. And so we're basically trying to find this distance. Mark it on here. You could just draw a separate triangle if you want to, but we're just trying to find this distance here, which I can call D. And so that's just Pythagoras. So D is equal to the square root of 45 squared plus 44.1 squared, which is 63 to 2 sig fig. So in mechanics, when you're using G, give your answers to 2 sig fig, but try not to get embedded rounding errors in a question. So I would use 44.1 there, not 44. 3 sig fig is allowed, but if you give your answers to more than 3 sig fig, you may well get penalised on the mechanics mark scheme. So this answer here would be better actually to 2 sig fig because G is to 2 sig fig. And so you're just demonstrating the degree of accuracy in your answer by doing that, but you only do that in mechanics. Everything else in maths needs to be 3 sig figure minimum, if not exact form, if it's pure maths. So yeah, hopefully that's enough for you to get on with the few anyway.